All right, 2x plus 3y equals 6. 4x plus 6y equals 12. So which method would work really great on 2x plus 3y equals 6? Okay, so you're talking about finding the x and y intercepts? I like to make a table when I do that, and then just put in a 0 for y. That'll be the x or y intercept. When I find the x coordinate, that'll be the x-intercept. I'll put in 0 for x also, and then the corresponding point is going to be the y-intercept. OK, so what happens, this one you just do in your head, guys. If you put in 0 for x, this 3y is gone, right? 3 times 0 is 0. And you're left with 2x. Can you see my cursor at all? Yeah, a little bit. I wish I could make it bigger. There's no way to make that cursor bigger unless you use a bigger pen. Yeah, it's kind of lame. 2x is equal to 6, which means x equals 3, because you divide both sides by 2. Okay, and then if likewise, if you plug in 0 for x, you get 2 times 0. That zeroes out. You get 3y equals 6, so y must equal 2. So I'm going to plot those 2 points, 1, 2, 3, 0, and 0, 2. Okay, just for the sake of argument, let's use a different method for the second equation. I mean, it would be best to use intercepts as well on the second equation, but let's not, just because it might be too obvious what the answer is going to be. So let's maybe solve it for y, just for fun. How do we do that? Okay, start by subtracting 4x. That gives me what? 6y equals negative 4x plus 12. And then what could you do? Divide by 6 and reduce the fractions. So you get y equals, okay, negative 4, 6x. What's negative 4, 6? Negative 2 thirds x. Plus 12, 6, 2. All right, shortcuts. What's the y-intercept? 0, 2. What's the slope? Yeah, you can think of it as negative 2 over 3 or 2 over negative 3. Either one's fine. Okay, so 0, 2 is right here. And what do I do to get back on the line? From 0, 2, I go down 2 and right 3. Uh-oh. I end up at the same 2 points that were on the other line. That means all the points are the same. So the lines coincide. So if I were to graph this thing, it's going to totally cover up the graph in blue, the first graph. If I aim right. So what does that mean about the intersection points? Yeah, the lines coincide, so every point is an intersection point. Lines coincide. They overlap. So every point, PT for point, is an intersection point. In other words, every point is a solution. Every point is a solution. Every point on the line is a solution. So how do you write the answer in that case? Well, okay, but that's true. Because there's an infinite number of points in the line. But you can't just pick and choose x and y coordinates. Not any x will work, not any y will work. They have to be x and y coordinates that satisfy the, well, both equations, which really reduce to the same equation when you simplify. So there is a way to do it using set builder notation. It seems kind of irritating when you first see it. But it's the only way symbolically we can write all the solutions. So really, I mean, pictorially, this is the answer, right? This line, every ordered pair on this line represents every ordered pair on both of these equations. That satisfy both of these equations, I should say. So pictorially, that's the answer. That picture is the answer. But how do you write it symbolically? That becomes important later on. Well, you use set builder notation, so you would say this. The solution is the set of all ordered pairs x, y. So you start with a curly bracket, write down a generic ordered pair x, y, and then a vertical bar. What does the vertical bar mean? Such that. So far, this is what I've written. It translates to the phrase, the set of all x, y, such that. Well, such that one of the equations is satisfied, because if one of them is satisfied, both of them are. So I'll just take the first one, such that 2x plus 3y equals 6. You could take either one, it doesn't matter. So this is just a fancy way of saying, hey, as long as x, y is on that line, it's a solution. The set of all x, y, such that 2x plus 3y equals 6. That's the mathy way of saying, hey, dude, any x, y on that line, any x, y that satisfies that equation is a solution. Okay? So what I did was I demonstrated the 3 situations you're going to come across in this section. And there's just a little bit of vocabulary to go with each situation. So let me back up to part A and tell you the vocabulary, vocabulary that goes with this solution. So remember in part A, we had a single intersection point. So guys, this single intersection point, graphically, that little point right there is the answer, right? Okay, when there's a single answer, then we say the system is consistent because there's at least one answer. So in this situation, we say the system is consistent. That simply means there's at least one solution. So let me underline that word and define it a little bit for you. That word means at least one solution. The system is consistent and independent. I'll contrast that. It'll be easier to understand where that comes from in the last example, so I'll just write it down for now. When there's a single intersection point, the system is consistent and independent. Well, remember in part B, there was no solution. So in that situation, we say the system is inconsistent. Because there's no solution. And then in the third example, where there's an infinite number of solutions, is there at least one solution if there's an infinite number of them? Yeah, so let me be clear here. This answer in the last example means that there's an infinite number of solutions. Because there's an infinite number of ordered pairs that make up the line, and every ordered pair on that line, whether you use the first equation to graph it or the second equation to graph that same line, every ordered pair is a solution. So there's an infinite number of them. So we would say the system is consistent, yeah? So the system is consistent because there's at least one solution. Let's back up. Okay, the system is consistent. If I could spell. And not independent, but dependent. So here's where that terminology comes from. If you solve, either equation for y, if you solve either equation for y, get y by itself, you end up with y equals negative 2/3 x plus 2. In fact, had I wanted to, I could have replaced that first equation that I took with this statement. The set of solutions is a set of all x, y such that y equals negative 2/3 x plus 2. It's equivalent to what I wrote previously. Now, there's an infinite number of solutions, but when you write it this way, y depends on what you choose for x. The value for y that you get depends on what you choose for x. So we call it a dependent system. I know, it doesn't seem important right now, and it's not that important right now, but later on, the terminology becomes very important.
Y depends on what?
Well, I mean, think about it. If you wrote the equation this way, and I asked you to give me a solution, then a quick way to get a solution would be to, say, plug in like 0 for x, right? So if you plug in 0 for x, then y depends on what you just plugged in. And in that case, it's 2, right? So 0, 2 would be a point on the graph. It would be a solution to the system of equations. So all I'm saying is the value for y when you write it this way depends on x, and that's where the terminology comes from, dependent versus independent. Okay? That's it for this section.